In this video, we will discuss one last application of the definite integral. Once again, this is a work example. And what we're going to be doing in this example is calculating the work done essentially in pumping water. And we're going to investigate two such problems. So for the work problems, we're going to have the ones involving Hooke's law, and then the ones involved pumping water or fluid out of a tank. And I say fluid because it could be something other than water. It might be oil or gas or something else. So in this problem, we're given a right circular cone as our tank. The tank is 10 feet. The radius at the top is 4. Find the work done in pumping the water over the top edge of the tank. So we're thinking that this tank is completely full, and we'd like to know how much work is required to pump the water out of it. Now, in order to set this up, I'm going to go back to the basics and think, well, we want to use a definite integral. So what we're going to have to do is think about, taking all of the water in the tank and dividing it up into a bunch of little thin slabs, and then think how much work is required on one of those arbitrary slabs. So when you do that and you break it up into a bunch of little slabs horizontally, you have kind of this arbitrary ith slab. And what we need to know is that if we're thinking about this as being, I don't know, let's put it in y because it's a height, y units up from the bottom of the tank, how much work is required to lift that thing to the top? And we're thinking that, the width of this is delta y. So I'm going to go ahead and just use the notation, wi equals the work required on this ith slab. So it's representing kind of just a arbitrary slice of that water. Well, in general, the work is going to be, we've said, force times distance. And if I can approximate what's going on this ith slab, then that's going to tell us exactly what function we need to integrate. So the force in this case, we're going to think of it as being the weight of that water. So this force is going to be the weight of the water. And in general, we think of weight as being volume times density. So we're going to have to take the volume of that little slice and multiply it by its density. And in the problem, we're given that the density of water is 62.4 pounds per cubic foot. And what we are going to do is just go ahead and we're going to use the symbol delta to represent the density. So at the end of the problem, we will substitute in 62.4. And let me note that this is the thing that would change if the liquid in the tank was something other than water. If it was, say, oil or gas or some other liquid, we would have to tell you what that associated density is. So in terms of this small little slab, we have to think, okay, if we are y units up, we need to determine its volume. So that is, I need to know for this small little slice here, what is its radius going to be? And if we look very carefully, just like some other cone problems we've encountered, there's really similar triangles in there. So you have this r and y, so y is measuring how far from the bottom of the tank. And then you have the entire height and the big radius of the tank, so 4 and 10. So similar triangles tells us that 4 over 10 is equal to r over y, which tells us that the radius is 2/5 y. So in terms of the volume of that little slice here, it's going to be the area of the top, so a circle, times its width, delta y. So its volume is going to be pi times 2/5 y squared delta y. And then we need to multiply this by its density, delta, and then we need to multiply this by the distance it is moving. So if we are at a height of y, how far do we have to move this water to get it to the top of the tank? Well, the entire length is 10. We're at y. So this remaining distance yet to move would be 10 minus y. And at first it might seem like there's a lot going on here, so let me try to make this as simple as possible. What we're doing is thinking about the work of this ith little piece, and the work is force times distance. The force is just the weight of that water. So it's volume, so we found the volume of that little slice, times density. So this entire thing would be its weight. Then we multiply it by how far it needs to move. And since we know what's going on this kind of general slice, we know that in general, the work is going to be the definite interval over how the y values vary. So they vary from 0 to 10. And we integrate exactly what we see above, where this delta y is going to become our dy, and then everything else is going to become the integrand. So we're going to have pi multiplied by 2/5 squared, so 4 over 25, multiplied by delta, those are all of our constants, the y squared, 10 minus y, and the delta y becomes a dy. So we pull those constants out, so 4 pi over 25. Inside, we think of this y squared as distributing, so 10y squared minus y cubed. So we anti-differentiate term by term, so 10/3 y cubed minus 1/4 y to the 4th, and we're evaluating from 10 to 0. So I forgot the density delta. So at this point, we can go ahead and plug in what that value is for delta, 62.4. So we are going to have 4 pi over 25 times 62.4. We plug in y equals 10, so 10/3 times 10 cubed is going to be 10 to the 4th over 3 minus 1/4 times 10 to the 4th. So 10 to the 4th over 4. We put a minus sign, we plug in 0. When we plug in 0, we get back 0. In this number we see here, it's not going to simplify all that nicely. We could certainly plug it into our calculator to get an approximation, is going to be the work. Because we are measuring in feet and pounds, it's going to be foot-pounds of work. So foot-pounds. So let's look at one more similar example, and just keep in mind this general procedure that we've used here. We're going to use that same exact procedure. So in this problem, we're asked to find the work done in pumping the water over the rim of a tank that is 50 feet long, has a semicircular end. So a semicircular end just means half of a circle, with the radius here of 10. So this measure would be 10 feet. Its height there would be 10 feet. And we'd like to find the work done in pumping the water out of the tank if it is filled to a depth of 7 feet. So let's go ahead and just think about what's going on in terms of just the end cap here. I want to draw that picture just a bit larger. So we have the bottom half of a circle of radius 10. So I'm going to go ahead and embed that in an axis just to give myself some scale to work with. So this would be 10 minus 10 minus 10. And if we think about the function that would represent this, the bottom half of a circle of radius 10. So that would be y equals minus the square root of 100 minus x squared. And what we would like to know is how much work is required in emptying out this tank if we're starting off with 7 feet of water in it. So if we have 7 feet of water, that means that the top of the water to start is at y equals minus 3. Okay, and we need to pump it up to the top. So starting out like we did previously, we said that what we want to do is take this tank and break it up into a bunch of little kind of sub-intervals and approximate what is going on each of them. So we're thinking, if we look at some small little slice, how much work is required to lift that up. So we're thinking that, this slice is at some y value. So we want to know what is the work to lift that ith slice to the top of the tank. So work is force times distance. So in force, we said, is really its weight. And to find its weight, what we are going to do is take the density of it. It's still going to be 62.4 as it was in the previous problem because it's water. We're going to take the length. So recall that this tank is 50 feet long. So we're going to have 50. That's going to be the length. And so it's going to be length. We're going to need to multiply that by width. And then we're going to need to multiply that by thickness. So in terms of our tank, what is the width going to be? Well, looking at it, this y value in this slice, we need to know what x value would correspond to it. And the most natural thing to do is to trace up and call that x. And then that entire width would actually be 2 x's because you would have x and x. So 1x, 2x. So the question is, what is x? Well, if we recall that we have the equation of a bottom half of a circle of radius 10 centered at the origin, x is going to be equal to the square root of 100 minus y squared. So the same exact thing that we used to come up with our formula for y in the beginning. And we have 2 x's. So that's going to be 2 times the square root of 100 minus x squared. 100 minus y squared. Everything's going to be in terms of y here. And the reason I know everything's in terms of y is looking at how we've broken this up is we've done so in terms of these horizontal slices. Then the thickness is going to be delta y. So it's a small thickness of the slice. And then we multiply it by the distance it has to move. Well, if it's at a y value here, note that it has to move up to y equals 0. So you take the larger value 0 and you subtract away the smaller value y. So the distance it has to move is minus y. So minus y is the distance. And at first glance, that minus y can seem quite troublesome. But let me note that if y is negative, like it is here, minus y is positive, and a distance moved should be a positive quantity. So now, let's go ahead and set up the integral. So the total work done then is going to be the definite integral over how the y values vary. So the y values are varying from minus 10, the bottom of the tank, to minus 3, because it was filled up 7 feet. And what we are integrating is we are going to have the 50 delta, then we have 2 square roots of 100 minus y squared. I'm going to write this as 100 minus y squared under the square root times minus 2y. So I've simply taken that 2 and put it with the minus y, and we'll see y in a moment. And the delta y becomes dy. Now what we need to do is evaluate this resulting integral. And in order to do so, I'm going to give myself a bit more space to work with here. And let's see here, we have the 50 delta, which pulls out, and then we have this resulting integral. And in that integral, I'm gonna go ahead and write it out again. We have minus 10 to 3 square root of 100 minus y squared times minus 2y dy. Notice that what we have under the square root, its derivative exactly appears outside of it. That's a key indication, the function derivative pair, that we should apply the substitution property. So u is 100 minus y squared. Du is minus 2y dy. So u du. But because it is a definite integral, we need to change our limits of integration. So if x is equal to minus 10, then u is equal to 100 minus 10 squared. So u is 0. For the upper limit, if x is 3, u is equal to 100 minus 3 squared, so 100 minus 9, which equals 91. So our new integral is going to be 50 times delta, and I'm just going to substitute in now delta is 62.4. The integral from 0 to 91 of the square root of u du. So after the substitution, this becomes significantly nicer looking. So we have the constant hanging around out front. Square root u is u to the 1/2. 1/2 plus 1 is 3/2. So we have 1 over 3/2, which is 2/3, u to the 3/2 from 0 to 91. So we plug in 91, put a minus sign, plug in 0. So 100 over 3 coming from the 50 times 2/3 multiplied by 62.4, and then we'll have 91 to the 3/2. And when we plug in 0, we get back 0. And because of our units here in terms of feet, this is going to be pound feet of work. And this gives us our solution. So once again, from a big picture perspective, let me know, these problems are, fairly intense, but what we have to do is think about, taking this water that we have, breaking it up into these horizontal slices and thinking how much work is required to lift that arbitrary slice. So force times distance, where force is given here as just weight. And its weight was the volume of that slice, here it was a rectangular slice with thickness, times its density, and then we multiplied it by how far we had to move it. Once you determine the work on that ith slice, this is exactly what you integrate. So the only difference is the delta y becomes the dy, and then everything else is copied down exactly. Once you have that definite integral set up, evaluate, you have the work done.